today's class, let us learn 3 more types of matrix representation of a graph: Cutset matrix, path matrix, and adjacency matrix of a graph. First one, Cutset matrix. Cutset matrix. If I have a graph G with m edges, m number of edges, and say q cutsets, then the cutset matrix is denoted as C. Each entry Cij is value either 0 or 1. It's a 0 1 matrix with the entry Cij equal to 1 if ith cutset contains jth edge. If ith cutset contains jth edge, then the entry Cij is 1, otherwise it is 0. Cutset matrix is a matrix 0 1 matrix. The entry is equal to 1 if ith cutset contains jth edge, and it is 0 otherwise. Suppose this is my graph G. Is like this. Graph on 5 vertices, say there is a parallel edge. We'll have a self loop 1 2 3 4 5. Edges are A, B, C, D, E, F and G. Okay. Suppose this is my graph. I'll name the cutsets for this graph. Cutset 1 C1, simply an edge A. C2, cutset C2, B and G, edges B and G. C3 is B, D and C. C4 is E, D and C. Then C5 is G, D and say C. Then C6, cutset 6 is edges B and E. 7th cutset is say G and E. These are my 7 cutsets for the graph G. Let us write cutset matrix C, okay, which has cutsets along the rows and edges along the columns. So 7 cutsets are there: C1, C2, C3, C4, C5, C6, C7, and the edges are A, B, C, D, E, F and G. Entry is 1 if ith cutset contains jth edge. This entry is 1 1 C1 1. C1 is a cutset which has got only one edge, that is A. So only this entry is 1, rest are zeros. cut set C2 has got an edge B and G. So entry B and G. Rest are zeros. Similarly, C3, B, D and C edges are there. In cut set C3, B, C and D, rest will be equal to 0. C4, like that I'll complete it. So this is the cut set matrix for the graph G. So when you have a cut set matrix, by looking at this cut set matrix, we can observe few things. If I do any permutation of rows or columns, then that just means that I'm relabeling the cut sets and edges. Okay, so permutation of rows or columns just corresponds to relabeling of cut sets and edges. And each row is a cut set vector, and if I have any column with all the entries equal to 0, suppose this, all the entries are equal to 0, that means that that edge forms a self loop. F here, you can see in my graph, F is a self loop. And if you find any columns which are identical, then that means they are parallel edges. So this column C with column D, you can observe they are identical, C and D. Therefore, I can say that these two corresponds to parallel edges. You can observe C and D are parallel edges. So these are the basic observations when you look at the cut set matrix. Now what happens to rank of a cut set matrix? Theorem says rank of a cut set matrix, that is C, is same as rank of incidency matrix A, which is nothing but n minus 1. Rank of a cut set matrix is same as rank of incidency matrix. Suppose I have non-separable graph. If my graph G is non-separable, then every set of edges which are incident on a particular vertex forms a cut set. Graph is non-separable means it's connected graph. So all set of edges which are incident on a particular vertex, they form a cut set. Therefore, I can say that every row of incidence matrix A is included as a row of cut set matrix C. Because see, when I consider incidence matrix, if all the edges are incident on this particular vertex, of course this set of edges will form a cut set. So I can say that every row of A of G, every row of incidency matrix A is included as a row in C. Therefore, I can say that incidency matrix A of graph G is contained in cut set matrix of a graph, right? And if I have a separable graph, then of course I can write its incidence matrix as a block matrix, and each block is contained in C of G. Even the graph is separable, A of G of each block is contained in C of G. So when this is the case, I can write rank of C is greater than or equal to rank of A. and I know rank of incidency matrix is n minus 1. Therefore, I can write rank of C is greater than or equal to n minus 1. Next, we know that number of edges in common to a cut set and a circuit is always even. Therefore, I can say every row in C is orthogonal to every row in B. B means fundamental cut set matrix, right? Number of edges common to a cycle and cut set is always even. Therefore, I can write every row in cut set matrix is orthogonal to every row in fundamental cut set matrix. Always remember, edges should be in the same order, provided the edges of B and C are arranged in same order. Therefore, I can say that B is orthogonal to C. That means B into C transpose is same as writing C into B transpose, which is congruent to 0 mod 2. Similar proof we have done in proving the number of in proving rank of B is equal to m minus n plus 1. That is there in my last video, that is class 27. So now from Sylvester theorem, I'm going to write rank of B plus rank of C transpose is less than or equal to number of edges. I'm considering it that as m. So I can write rank of C transpose is same as C, rank of C. Therefore, rank of C is less than or equal to m minus rank of B. Rank of B is m minus n plus 1. That I have proved in my last video. So that rank of C is less than or equal to n minus 1. We've already proved rank of C is greater than or equal to n minus 1. Now proved rank of C is less than or equal to n minus 1. Therefore, I can say rank of a cut set matrix is equal to n minus 1, in fact, which is nothing but rank of incidency matrix. Next is another 0-1 matrix, which is often used in communication and transportation networks actually. That is path matrix. Path matrix. This is defined for a specific pair of vertices in the graph, say x comma y. Particularly, say suppose these two are my vertices. Then path matrix is defined for the specific vertices of a graph, and I'm writing path matrix of P of x comma y like this, and rows in P of x comma y corresponds to different paths between the vertices x and y, and columns corresponds to edges of the graph G. P of x comma y, entry say Pij, each entry Pij is 1 if ith path contains jth edge, or I can say jth edge lies in ith path, then the entry Pij is 1 and 0 otherwise. So remember one thing, always the path matrix is defined for a particular pair of vertices. Suppose I have graph like this. Vertices 1, 2, 3, 4, 5, 6, edges A, B, C, C, D, E, F, G and H. Now suppose if I consider a vertex 3 and 4, vertex 3 and 4, between 3 and 4, say there are 3 different paths I can say. One is HE, another is HGC, and there is HFD and C. 3 different paths between P1, between the vertices 3 and 4. First path is, which includes the edges H and E. Second path between the vertices 3 and 4 is H, G, C, H, G and C. And the third path includes edges H, F, D and C. Okay, these are 3 possible paths between the vertices 3 and 4. So I'll write P of vertex 3 and 4. You can even write to V1, V2, V3, V4 like that, so that you can write P of V3, V4. So rows corresponds to the different paths between the vertices, and columns corresponds to the edges of graph G. Okay, P1, P2, P3, edges A, B, C, D, E, F, G and H. Path 1 between 3 and 4, the edges H and E are included, so H and E. Rest all the entries are zeros. Then P2 includes H, G and C. So no other edges are included in path P2. In path P3, H, F, D and C. Rest entries are zeros. This gives you the path matrix between the vertices 3 and 4. We can make few observations from this path matrix. If I find any column with all the entries equal to 0, then that means that that particular edge does not belongs to any of the paths between the vertices 3 and 4. Okay, or between the vertices say x and y. A column of all zeros here this, if I consider this and this, a column of zeros corresponds to an edge that does not belongs to any of the part between x and y, and a column of ones corresponds to an edge that lie in every path between the vertices x and y. Here this edge h, which contains all the entries equal to 1. A column of ones corresponds to an edge that lie in every path between the vertices x and y. And of course there is no row with all the entries equal to 0. That is not possible to have. And ring sum of any two rows of path matrix corresponds to a circuit or edge disjoint union of circuits. Next is one more type of matrix, in fact an alternative way to write the incidence matrix, that is adjacency matrix. This is sometimes more convenient to represent a graph by using this adjacency matrix, or we say connection matrix. Adjacency matrix of a graph G with n vertices and no parallel edges is n cross n symmetric matrix. Of course the entries are either 0 or 1, and the entry xij in adjacency matrix is 1 if there is an edge between ith vertex and jth vertex. If there is an edge between ith vertex and jth vertex, then the entry will be equal to 1 and 0 otherwise. Xij entry is 1 if there is an edge between ith and jth vertex, and 0 otherwise. So the matrix is denoted by X of G, adjacency matrix or connection matrix X of G. Entry is 1 if there is an edge between ith vertex and jth vertex. Suppose this is my graph, say suppose this is my graph on 6 vertices, V1, V2, V3, V4, V5, V6 and even E2, E3, E8 are the edges. Adjacency matrix for this graph is denoted by X. It's n by n matrix. Here number of vertices are equal to 6. Therefore, it's 6 cross 6 matrix. I'm taking vertices along rows and along columns also. So V1, V2, V3, V4, V5, V6, V1, V2, V3, V4, V5, V6. Entry is 1 if there is an edge between ith vertex and jth vertex. There is no edge from V1 to V1 itself, therefore entry is 0. V1 to V2, there is an edge. Then V1 to V3, there is no edge. Between V1 to V4, no edge, no direct edge. V1 to V5, there is an edge. V1 to V6, there is an edge. Similarly, between V2 to V1, there is an edge. V2 to V2, there is no edge. Like that, I will complete the. This is how it looks. Adjacency matrix of a graph G. Observations which we can make immediately by looking at this adjacency matrix X of graph G are like the entries along the principal diagonal of X are all zeros if and only if graph has no self loop. If the graph has no self loop, then I can say these entries along the principal diagonal are equal to zeros. So a self loop at particular vertex, say at ith vertex, if there is a self loop, then the entry xii, if there is a self loop at ith vertex, then the entry xii will be equal to 1. Okay, if there is a self loop at particular vertex vi. Then the definition of adjacency matrix makes no provision for the parallel edges. This is why the adjacency matrix X is defined for graphs without parallel edges. Okay, there is no particular way of representing the parallel edges in case of adjacency matrix. So that can be adjacency matrix can be written only for the graphs with no parallel edges. If the graph has no self loops, of course no parallel edges, then the degree of the vertex is equal to number of ones corresponding to the particular row or particular column. Number of ones gives you the degree of the particular vertex. Again, permutations of rows and of the corresponding columns simply implies reordering of the vertices. If the graph is disconnected, then again this adjacency matrix can be written in block diagonal forms. So if any square symmetric binary matrix is given to you of order say n, then we can always construct a graph. If binary matrix, of course it has to be symmetric binary square matrix is given to you, then you can write the graph for the corresponding matrix. These are the observations of adjacency matrix.